So we're moving on to section 9.5, which is hyperbolas. Now, hyperbolas are very similar to ellipses. The only difference is in the equation, which we'll look at later, instead of adding our x squared over a squared and y squared over b squared equals 1, we're going to be subtracting them. And that actually changes the look of our graph a little bit. But overall, there's a lot of similarities between them, a lot of similarities in vocabulary and things like that. So we're going to go over some right now. All right. So it says, similar to an ellipse, a hyperbola. So we say that hyperbola, okay, is the set of all points that are an absolute value from some constant value. And those values, again, are called foci. So these also have two focus of foci in hyperbolas. Okay, so every hyperbola has two axes of symmetry. There's the transverse, make sure I get that. Yep, transverse axis. And there's also called the conjugate axis. Okay, and these axes are perpendicular at the center of the hyperbola. Okay, so there is going to be a center, but it's like there's not really, there's a point, but not really. Okay. All right, and the foci are always lie on the transverse axis. So the transverse, the longer of the two. Okay, so the endpoints of the transverse are the vertices. Remember, the vertices are the ones that are a little bit farther away from the center. And then the conjugate axis is like the shorter one, and we called those covertices. Okay. All right, so here's what they look like right here. Ready? Okay, so a hyperbola that opens up like this, okay, like this, looks like two C's, okay, is centered at 0. That's one of those horizontal ones, okay. Notice the foci are not located inside, right? They're located outside of our endpoints. So generally, remember, we had foci that were a little bit less than the endpoints. Now we have them a little bit more than the endpoints. And then we also have those covertices, right? And the covertices are at the end of the conjugate axis, right? And then the next one below it is an example where it's like up and down, right? Kind of like up and down like that. And again, the foci are longer or farther away than the endpoints from the center, okay? All right, now you'll notice something about both of those graphs that you didn't see in ellipses, and it's those red like dotted lines basically. Well, those two lines actually are special. They're asymptotes, meaning that our lines get super, super close to them but never touch them, right? So what it's saying is this goes on forever, and this graph kind of goes on forever, very similar to it, but it never crosses it, right? The same is true of this one. It kind of goes on forever like this and kind of goes on forever like this. They get super close to it, but they never touch it. Same is true with vertical ellipses as well. Okay, so let's look at our equation. So if we look here, right, we notice that it's very similar to an ellipse equation. The only difference, again, like I said, is there's a minus sign there. Okay, same with, okay, vertical ones, minus sign, y comes first. Remember, a is still, 2a is the length of the transverse axis, and 2b is the length of the conjugate axis. Here's what's important, okay, our asymptote equation. Plus or minus, there's two of them, plus or minus b over a times x. So if they give us our asymptote and they give it to us as some equation, obviously you'll notice that both of those cross at the center 0, 0, right? But if we can figure out what b and a are, or they give us a slope, we can figure out what b and a are for our equation, right? That's kind of nice. That helps us out quite a bit. Again, the foci are at C, and they have the relationship much like the Pythagorean theorem. Again, the difference between ellipses, where it was c squared is a squared minus b squared, with hyperbola, it's c squared equals a squared plus b squared. And you'll notice that is like the Pythagorean theorem. Excuse me, that's the theorem I was saying. So that's the Pythagorean theorem right there. It actually helps us out quite a bit, which is kind of sweet. Okay, so let's take a look at an equation. So our first example. So it says, write the equation of this hyperbola. Okay, so first off, it's centered at 0, 0. That helps us out, right? Now, we also see that our endpoints are at 4, 0 and negative 4, 0. So we know that the value of A, right, from the center out to my endpoint is 4 units. So we know A is 4. I also know that C to my foci is actually going to be 5 units. So 0 to C, or 0 to C is going to be 5 units. So then we can use that information to figure out what B is, right? We said it's of the form C squared is equal to A squared plus B squared, right? So I have to solve this out, and I'd say, well, 5 squared is equal to 4 squared plus B squared. Okay, so 25 is equal to 16 plus B squared. I subtract 16, I get B squared is equal to 9, which means if we take the square root, we find that B is equal to 3. Okay, so that helps us, right? That helps us. Once we know B, we know A, we know how to write the equation of our ellipse, right? So let's do that. Let's write the equation. So we said, okay, so that one was a horizontal one, which means x squared comes first. So it's going to be x squared over a squared, which was 16, minus, instead of plus, y squared over 9, because we said b squared was 9, equals 1. Okay, so there's the equation of our ellipse, right?